All right. Hey, where's my mother frickin' breadboard? There it is. One 1.5, 2.2, and 5.6. Brown, green, red. Brown, green, red. Red, red, red. Red, red, riding, red, red, riding, red, red, riding, red. Green, blue, red. That's pretty. Okay, so here's my circuit. you guys able to see that okay on your computer screen? I know that projector image is not very good. But on your screen, can you see it okay? That's how I'm setting mine up. And you can visualize how that's a parallel circuit, right? So here's this. So, put my power supply on these ones here. And then can I read resistance across those resistors, just how they sit for part one? I sure can. So it's going to have you go through and measure the resistance of each resistor. It's going to have you hook up your circuit, 12 volts, and read voltage across each resistor. I'll show you with my digital multimeter. What that looks like. So, in a parallel circuit, what remains the same? Voltage remains the same, and then the current across each branch is that going to differ? Yes, it is, depending on the resistance. The voltage across each branch is going to be different. So if I put my channel 1 to 12 volts, turn channel 1 on, I read, and to end, I've got 12 volts running through this circuit. What would I have across each branch? So across each resistor, how many volts should I have? Parallel circuit, so I should have 12, right? Oh, 12. Oh, 12. Oh, 12. Perfect. Now, how can I calculate what the total current is and what the current across each run would be? Any ideas? No? Okay, let me tell you, since you're such a lively crowd today. Okay, R1, 1.5 kilo ohms, how many volts? R2, 2.8 kilo ohms, how many volts? R3, 5.6 kilo ohms, 12 volts. So the current across on each branch we can find by using, we've got resistance and we've got volts, and we need to find I, current. I R1 equals ER1 over resistance of R1. I'm just going to put R1. So in this case, it would be 1,000 or 12 volts divided by 1,500 ohms. You all understand that when it says kilo ohms, that's 1,500 ohms, right? When we're using Ohm's law, you have to keep the units the same. So you could either say, if you wanted to use 1.5 kilo ohms, you would have to convert 12 volts to kilovolts, right? But I just assume keep it amps, volts, ohms. That's just the easiest way for me to keep things straight. But are you guys having any trouble with the units and decimal places? Do we need to go over that? Are you guys okay? Okay. All right. So what's this one going to be? So 12 divided by 1,500. 8 milliamps. So 0.008 amps. So that's R1. IR2 is going to be 12 divided by 2,200. IR3 is going to be 12 divided by 5,600. So total current, if I add those up, is 15.6 milliamps. I total equals IR1 plus IR2 plus IR3. Zero point zero one six amps. 0.56. Is there another way we could calculate that without calculating the current across each branch? Why, yes, there is. Good answer. Okay, so how can we do that? What is 12 volts in this circuit? Is that the total voltage? We want to know what total current is. So we can either do this. Total resistance, yes. What the hell is that? What's going on? So how do you find total resistance without measuring it? Cannot add them up in a parallel circuit. There's a formula. Have you guys learned it yet?
Yeah. I just don't have it.
It's the reciprocal formula.
Yeah.
So if you have two resistors, you can do product over sum. But this works all the time, whether it's 2, 3, 4, 10 million. Our total is going to be 1 over the sum of 1 over R1 plus 1 over R2 plus 1 over R3. If I calculate this out, we should come pretty close to 0.0156 amps. So 1 over 1500 plus 1 over 2200 plus 1 over 5600. I'll pull up my calculator so you guys can see how I do that. So we got we don't have any parentheses on this. Boom. 1 divided by parentheses 1 divided by 1500 parentheses oh, backspace, damn it. Start over. 1 CC 1 divided by parentheses, 1, 100 plus 1 divided by 200 plus 1 divided by 5600 parentheses equals. That's not right.
That's what I got. That's what I got as well.
769 ohms.
And it's less than the least value or resistor.
Oh yeah. Oh, this is what. Okay, that's right. It is right. I'm thinking we need like milli ohms. Never mind. I'm sorry. I'm effed up today. All right, 769.36 stuff. So we got 12 volts. What should I be? E over R. E total divided by R total, just Ohm's law, equals 12 divided by 769.36 equals. I think we're going to get about 15.6 milliamps.
Yep.
Sure enough, whoops, 12 divided by 769.36. Boom. Isn't that cool how that works out? Math and Ohm's law. So total current should be 0.0156 amps. I know that's a lot of scribbling all over the screen, but did everybody follow that?
Makes sense.
All right, I'll let you guys have at the lab. Let me know if you have any questions. Have fun. Make this the best day ever. So what would happen if we added another resistor in there? What would happen to the current? Chaos would ensue. Fires would start. This is important. Very, very, very important. And the more you guys do this, the more you see it, the more you'll grasp it. But I have a voltage, and I have resistance in a circuit. If I add more resistance in parallel, what happens to the total resistance? Goes down. Think about it. I'll get back to this. What happens to the total resistance? It goes down. What happens to the total current? Goes up. So you add resistance in parallel, and your current goes up. It's very, very important because a lot of most of the industrial applications you see, everything's wired in parallel. All these lights in here, are they wired in series or parallel? Parallel. So what happens if you add more lights to a circuit? What happens to the current? It goes up. So you get to a certain amount of lights in your circuit, you're going to start tripping a breaker?
Yeah.
Yep. What about the old-fashioned fuses? Remember when I showed you those on that old panel? You start blowing a fuse?
You put a penny in there.
Yeah, so you put a penny in or a bigger fuse, right? No. The fuse is doing its job. It's telling you there's too much current for this wire. The wire is going to burn up if you keep adding things to the circuit. The fuse is doing its job. So you put a bigger fuse in there, you put a bigger breaker in your panel to handle more load without upsizing the wire that's feeding that circuit, you're going to have a house fire, right? So that's why it's important to know what current does in a circuit in parallel. One more demonstration that I'll do. You guys need this scribble all over the screen? I'll leave it up and I'll come back to it. Remember at the beginning when we started talking about Ohm's law, I told you about the water pipe analogy? You recall that?
One of the first days.
Yep. So think of it this way. I got a pump pumping some wah-wah through some pipes. All right. So current is flowing this way. I got some resistance to current flow, the friction on the pipe. But that pump is a 12-volt pump. And we're pushing that much, putting that much force on the water, making the water go through the pipe. Do you think current flow, so it's the amount of water flowing through one point at any given time, is going to go up or down if we add some branches in here? Current's going to go up because it's got more places to push that water through, right? See what I'm saying? So now we've, bless you. You got the vid? Just kidding. No.
I don't think so.
Now we've got more places to push the water through, right? We got another pipe here. And let's add, for kicks, let's add another one. Got another pipe here. And it's a smaller diameter pipe because I can't draw, but that's cool. It's a good example. So now we've got these extra pipes here for the water to flow through. Current's going to go up because now it has options, right? I can go this way. I can go this way. You see, can you kind of visualize that? How now current's going to go up because there's less resistance. There's more places for it to go. Does that make sense? So that's kind of how a parallel circuit works. All right. How do I get back to my stuff? I guess I lost my annotations, but do you guys need the math shown again? I can put it back up there. All right, well, I'll put some, since you guys won't say a word today, I'll put some music on and I'll do the math again up on the screen on the whiteboard here. Okay? I just want you guys to be happy. Are you happy?
Yep.
No, you're not. What do we want to listen to today? Huh?
Anything but country.
Anything but country? I mean, I keep doing 90s because it seems like something everybody can kind of, but then you also get like Madonna and all that other stuff in there too. So, any other suggestions? 90s rap? Celine Dion? Some Yanni? You want to listen to Yanni? No?